Okay, we were talking chapter 12, and we are talking about really last time bonding, and we got into drawing Lewis structures for covalent bonding. And as we talked about, there's some steps that you really should follow when you're drawing these that will lead you to the correct, hopefully, structure or a really good structure. So you're supposed to kind of work through these last time. So let's go through them, and then we'll kind of talk about, obviously, the steps that you need to follow. So we'll start with the SO2. So remember, one of the first things you want to do is count up the total number of valence electrons, which obviously equals the group number. So sulfur is group 6. There's 2 oxygens, which is also group 6. So that's like 18 valence electrons. Once you have that, right, you want the logical arrangement as to how these are hooked up to help you decide. Usually the center atom should be the least electronegative. That means that fluorine should never really be in the center. Also, hydrogen shouldn't be in the center because, again, it will have too many bonds, too many electrons. So when we look at the periodic table, sulfur and oxygen are in the same group, and oxygen is actually further up, and that means it's more electronegative. So sulfur should be in the middle, oxygen should be around, and you could go up and down if you want, or side by side. Once you have that logical arrangement, remember what you want to do is just do a single bond to everybody from the center atom. That's going to use up 4 electrons in this case, as each line represents a bond and 2 electrons. We then have 14 more electrons. Those extra electrons, as we talked about, will go on as pairs of electrons, so dots. And we always kind of work the outside in when we're doing that. So we got 2, 4, 6, 8, 10, and 12. At this point, I've now put 16 electrons on it. I still have 2 more to go. Once we fill up the outside ones, then we go to the center, and we'll fill up the center there. And that is how those dots get there, and they should be there, by the way. And that is how they should actually sort of end up there. At this point, we put 18 electrons, and after you distribute all your electrons, and as we talked about, you want to kind of think about it when you're doing these sort of structures as the electrons maybe not belonging to somebody in particular, that you want to kind of spread them out equally kind of over everybody and distribute them that way. We want to make sure that everybody has met the octet rule. In this case, hopefully you can see that it is the sulfur here that has not met the octet rule. The oxygens are good. They have 8 electrons around them. So at this point, what we want to do is try to fix that. And we want to fix it by first making a double bond. And remember that when we make a double bond, we're not just going to draw the bond. Otherwise, you'll end up with too many electrons. But we're actually going to take a pair of electrons and kind of bring them in to make the double bond. And in this case, you could actually do it on either oxygen, as they're both the same. So we're going to take a pair of electrons, drop them in, and that will get us now a double bond here to the right and a single bond here to the left. This is also something that can be a resonance structure, where we could have double bonded there to the left and left a single bond over there on the right. Remember, resonance structures are structures that happen when you have pretty much more than one location where you can put that double bond. And those are delocalized electrons. At any point, they could be at one oxygen or the other. So they're kind of moving around. So we could draw equivalent sort of resonance structures for it. Question on that one. So again, this is what it should look like. No common double bond on both sides that people like to do. It should not have that. Next is H2S. So again, hydrogen is group 1, and there's 2 of them. And sulfur is group 6, so that is 8 valence electrons. Once again, here, hydrogen can never be in the middle, so that leaves sulfur in the middle. Hydrogen's on the outside. Once again, a single bond from the center to each of the outside ones. That gives me 4 electrons in this case. 4 more to go. Are we going to put dots on hydrogen? No. So again, unless you want a big X, never put dots pretty much around hydrogen or anything like that. That means really the next place we're going to go is to the center atom, and we're going to put our electrons there as non-bonding electrons or lone pairs around the sulfur. And at this point, the sulfur now has 8 electrons. Each hydrogen has 2 electrons. And again, remember when you look at the periodic table, hydrogen just needs to get to helium, which is 2 electrons. So that is, again, why it should never really go over 2 electrons as well. Any questions on that one there? All right, continuing on here. We'll do N2. N2 is nitrogen, so there's 2 times 5, that is 10 valence electrons. In this particular case, there's actually only 2 atoms involved. You can still do it the exact same way as you do everything else. In this case, you just go side by side here and just do a single bond. So that, again, that is 2 electrons. We'll fill up the outside, so 4, 6, 8, and 10. At this point, we can see hopefully on the left-hand side that nitrogen has only 4 electrons, so it is short. The nitrogen on the right-hand side is all good. It actually has 8. So we want to try to fix that. So we're going to try to fix it by making a double bond. We're going to bring some electrons in to do so. That will then get us something that looks like this, perhaps. And in this case, did it fix the nitrogen on the left? It did not. It got better, right? It's now at 6 versus 4. It is still not at 8. So at this point, there's really no other place you can do a double bond. So your next option now is to roll into a triple bond. And it works the same way. We're going to take another pair of electrons and basically bring them in to get to our triple bond. And at that point, we will end up with our triple bonded nitrogen, which is why it's triple bonded. And at this point, it will now have obviously 8 electrons on each side through the sharing of those electrons in the triple bond. Question on that one there. Next is NH4 plus. So once again, nitrogen is group 5. There are 4 hydrogen, which is group 1, or 1 valence electron. And again, the positive charge here means that it has lost an electron, so we do need to subtract that off from our total. Just like if we had a negative charge, we would need to add that to our total. So that plus 1 results in it being subtracted. So that's 9 minus 1, which is 8 valence electrons. Once again, here our hydrogen cannot be in the middle, so that leaves nitrogen as the one that should be in the middle. We're going to do 1 bond, 2 bonds, 3 bonds, 4 bonds, and dare I say that is 8 electrons. So that makes the nitrogen in the middle good, and each hydrogen has 2. Typically, if it is a ion, we do put brackets around it and kind of put the charge on the outside again to indicate that it is. That is a polyatomic ion, which is something that's covalently bonded, but still has a charge. Any questions on that one there? Lastly, we got a little CO3 2 minus. So again, that is 4 for the carbon. There are 3 oxygens, each has 6. In this case, we do have a minus 2. So minus means it has gained electrons. 2 is how many it gained. We need to add that in, 18, 20, 24 valence electrons. Once again, if you look at the periodic table, carbon and oxygen are in the same row on the periodic table, and oxygen is further to the right, which means it's more electronegative, and that would mean that carbon there has to be in the middle. So we'll put carbon in the middle. We'll kind of put a little oxygen action around it. Again, we're going to connect with a single bond. That is going to be 2, 4, 6 electrons. Putting the outside ones on next. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. At this point, I have now put on there 24 total electrons. Everybody is good except our carbon here. And again, our carbon is short 2 electrons. So again, we do need to make a double bond. All 3 of those oxygens are identical or equivalent, which means you can make the double bond at any of those oxygens. Again, we're just going to bring in those electrons to do so. And that would get us, for example, a structure that looks like this. And again, we'll put some brackets around it there and the charge. We also could have double bonded there to the right, which would give us a structure that looks like this. Again, another resonance structure, and we actually have 3 in this case, where we could have double bonded there to the left in that case. And again, resonance structures are sometimes separated by these arrows. Once again, it is those double bond electrons, for example, that are moving around from one oxygen to the next. So at any given point in time, they may be at any of those oxygens. So not one structure by itself really describes what's going on. So that's why you could draw these sort of resonance structures as they're all sort of equivalent. Again, a reminder that if you're just asked to draw a Lewis structure, any one of those 3, for example, carbonate would be acceptable. If you're asked to draw the Lewis structure and all the resonance structures, then you should draw all 3 of them. Yeah. Any questions on how to draw Lewis structures or anything like that? Again, you do want to follow these steps. It should get you to the right picture. If you try to do, again, piecework, usually people end up with too many bonds, not enough bonds, too many electrons and stuff like that. Any questions on how to do that there? Yeah. So we talked about resonance here, but we're going to talk a little bit about bond length, and you don't need to memorize these numbers at all. But if we look at a carbon-carbon single bond versus a double bond and a triple bond, what we actually see is the single bond is actually longer. And then as you put on another bond, what happens is the 2 atoms actually get closer to each other because they get squished together. As you put a triple bond on, everybody moves closer. We see that also with carbon and nitrogen, 143 for our single, 138 for our double, and 116. So basically, every time you put kind of that more electron density in the middle of the 2 atoms, greater negative charge in the middle to that positive nucleus, just pulls everything closer together, and they're not as far away, the 2 atoms, from one another. That does relate to bond strength, and a triple bond is stronger than a double bond, and a double bond is stronger than a single bond. It is not like a triple bond is 3 times as strong or anything like that, but a triple bond is definitely stronger than a single bond. I think of it like a pencil, right? If you get a brand new pencil right out of the box, it's nice and long. You can take that thing and snap it all day, right? No big problem. You take a chemistry test and all you got left is like a nubbin of an eraser and just a little bit of lead. It's super small. Good luck trying to break that, right? And in half, it's just too close together. Everything's really held tightly. And then again, that's sort of what happens with the bonds. As that triple bond, for example, gets everybody closer, they're going to be held tighter. It's going to take more energy to try to break it apart. Now, resonance structures, as I mentioned, as we saw when we were drawing these, again, are one or more sort of Lewis structures that are drawn. And usually arises when you do have that option of equivalent places that you could double bond it at to kind of fix the octet rule, like we just saw in carbonate, like we also saw with SO2. Again, because those electrons are delocalized, you could draw more than one Lewis structure to sort of adequately describe what's going on in that bonding situation. And again, those arrows are usually used for it. So obviously the one we just did, here's another example, which is ozone. The charges on it, don't worry about it, but ozone could have a double bond over here, but it could also have a double bond over here. And again, they're essentially equivalent structures. The true structure is probably somewhere between all those resonance structures in terms of where those electrons are. There's our carbonate one we just drew. Benzene, if you take organic chemistry at some point, you will draw a lot of benzene rings. Benzene is basically carbons at each of these locations, although you usually don't draw the carbons. And each one has basically a hydrogen attached to it. And it actually has 3 double bonds in it. So usually you will see it drawn like so. You may also see it drawn like so. And sometimes in some books, maybe if you don't take real organic class, sometimes they'll just draw like a little circle in the middle to indicate that those double bond electrons are basically moving around, and it could be pretty much either the guy on the left or the guy on the right. So sometimes people will draw benzene with that little circle. And again, it still has the 3 double bonds just to sort of indicate that it could be on either side there. Any questions with that there? All right. Let's get this one here that we did. So in this class, obviously, everything that we do will follow the octet rule. But in real life, there are exceptions to the octet rule. So for this class, what you'll need to know is what the exceptions are. But you will never be asked to draw anything that doesn't follow the octet rule. So everything should follow the octet rule. We'll say not following the octet rule for when you take 1A. Then you do like nothing but things that don't follow the octet rule. So here, everything will do it, but in real life, there's kind of 3 exceptions that could happen. One is what is known as an incomplete octet. There are certain elements that are perfectly fine with less than 8 electrons around them. They're sometimes referred to as being electron deficient because they're missing some of those electrons. Beryllium, aluminum, and boron are usually the ones that we associate with that. And I would say probably in reality, boron is the one that you see the most, because really kind of beryllium and aluminum are kind of metals, and they usually do like a ionic type situation. So boron here in boron trifluoride, it has just 6 valence electrons and is perfectly fine that way. And again, that's what's referred to as an incomplete octet, basically less than 8. Another couple of exceptions that you sometimes come across, an odd electron molecule. That is basically someone that has an unpaired electron. So like we see here in NO, it actually has an unpaired electron. NO2 here, also an unpaired electron that happens. Sometimes they're referred to as free radicals. It happens there in atmospheric chemistry a lot with chlorine. They're very, very reactive because they have an unpaired electron. They don't really want to be that way, so they want to kind of react to fix it. So they're very, very reactive type of molecules. So an odd electron molecule is another exception to the octet rule. And then probably the one that you will definitely come across the most in your chemistry career, especially when you get into 1A, is the expanded octet. And the expanded octet means that there are certain ones that could actually go above 8 electrons. They could actually go upwards of like 12 electrons around it and be perfectly good with that. And that usually happens on the periodic table where you see sulfur. If you go to where sulfur is, go to the right, go to the left, and pretty much go down in the non-metal region of the periodic table, they can basically go above 8 electrons. The reason for that is sulfur's on period number 3. And period number 3 relates to n is equal to 3, the 3rd principal quantum level. And on the 3rd energy level, what orbitals do we first start to see? Yeah, that is where we first start to see d orbitals. And although they may not be using those d orbitals, they have them available to them to actually stash all the extra electrons if they need to. So they're able to go above it. With that being said, if you hit somebody on the periodic table, for example, in the nitrogen, oxygen, fluorine period 2, period 2 should never go over the octet rule because they do not have d orbitals available to them. They max out at p orbitals. So they can never go over it, but sulfur and below, sulfur right and left and below can go expanded octet. As an example here, our SF6, if we were just to draw the connection, I'm not going to draw all the non-bonding electrons on the fluorines, but if we roll around over here, it has 2, 4, 6, 8, 10, and 12 electrons around it, and it's perfectly fine. That is why you sometimes will see, for example, if you drew something like sulfate and you followed our picture and our rules, you really should, in this class, end up with a picture that looks like this. And everybody has 8, it meets the octet rule, everybody's single bonded. you Google it up or whatever it may be, even though maybe you're not supposed to do that. And you see this picture and you draw it on your paper, and then your teacher knows you did that because they didn't teach you it in this class, right? But you end up with this picture right here that disappears. And what we see here is 2, 4, 6, 8, 10, and 12 electrons around it, and it's actually perfectly good. Believe it or not, in this particular case, for reasons we don't talk about in this class, like formal charge, this is actually the better picture than this one. But that's not always the case, and we won't talk about how you determine that in this class, but you will in 1A. But that is, again, why if you kind of Google it or look it up somewhere online, you will sometimes see that picture for sulfate, and it's because it's actually a better structure, and it can go above 8. But once again, in this class, you probably should end up with the guy on the left because we're going to obey the octet rule in this particular class. Any questions on that there? So once again, you're not going to be required to draw anything that does not obey the octet rule, nor should you draw anything that goes over the octet rule. But you do need to know what those 3 exceptions are. Okay. All right, we're going to then talk about geometry here. And when we talk about molecular geometry, we're actually going to talk about 2 types of geometry. We're going to talk about electron pair geometry. And for the purposes of this lecture, I'm just going to abbreviate that as EG for electron geometry. And we're also going to talk about molecular geometry. And that is sometimes referred to as the shape. And for this lecture here, I'm just going to abbreviate that as MG for molecular geometry, so I don't have to write it out so much. So let's talk a little bit about this. What we're talking about is really the 3-dimensional arrangement of the molecules in 3-dimensional space. And it really is based on, always when you're doing geometry, it is based on the central atom and really how many electron pairs there are around the central atom and how many bonds there are. Those are really the 2 main things that you want to look at. And once again, we always look at only the central atom. That's really the only important one. Now, and there you can have 2 central atoms, and then you would look at them actually separately, but it's always the central. None of the outside atoms really determines the geometry or anything like that. It's always the one that's in the middle. So as long as you know, really, like I said, how many electron pairs and how many bonds there are to that central atom, you basically can figure out the geometry. The good news or bad news with this is it's just really for most people memorizing sort of the combinations to come together because most people can't kind of see it in 3-dimensional spaces in their head. The basis of this idea is, frankly, there's electrons involved in bonding and there's electrons involved in non-bonding electrons, obviously. And ultimately, electrons near electrons, they do not want to be near each other because they're both negatively charged. So what happens is they try to get away as far as they can from one another. Unfortunately, they could only go so far because they're kind of also locked into a bond, so they just can't get away. So what it does is, as they're moving around to try to find a comfortable sort of arrangement in terms of distance between the electrons, it actually ends up changing the shape of the molecule in some cases, and we get some different geometries of how the atoms end up and how the overall molecule ends up in 3-dimensional space. This is what is known as VSEPR, which stands for valence shell electron pair repulsion model. That is a mouthful, hence the abbreviation I'm imagining. When we do geometry, it's again about the central atom, and it's really broken up into 2 categories. One is where there are no non-bonding electrons or lone pairs on the central atom. So basically, if you drew your central atom, there are no dots basically around the central atom. And ones where they do have non-bonding electron or lone pairs, that would be you drew the central atom there and you end up with some dots around it. And depending on whether or not there are sort of the dots or no dots, the non-bonding electrons or the only bonding electrons will determine sort of the names of like the electron pair geometry and the molecular geometry, whether or not actually that they will be the same or different names that occurs. Probably the most important rule when you're doing geometry is pretty much when we're counting everything basically just counts as 1. So in the case of doing geometry, everything counts as 1. So If you got a single bond, if you got like a double bond, if you got like a triple bond, hey, if you got a pair of electrons, everybody here counts as one electron pair. It doesn't really matter. Now, in addition, obviously, when we're talking about bonds, if you have a single bond, double bond, or triple bond, they all count as one bond. So basically, everything counts as one. It's kind of like that activity maybe you did where they threw out the old school name of steric number. Everything counts as one. Basically, it doesn't matter if they're dots, doesn't matter if they're lines, 2 lines, 3 lines, double bond, single bond. Everything basically is one. The second consideration is if you were to draw some resonance structures, several different Lewis structures for something, because they're related to each other, if you did this geometry to each of the resonance structures, you would most likely end up with the same geometry, no matter which one you kind of did it to. All right, so let's just take a look at this. First off, the simplest geometry you could ever have in your life is a diatomic molecule. So in a diatomic molecule, you basically just have two atoms. So when you have two atoms, the only way basically you could connect those guys is in a straight line, right? The shortest distance between 2 points is a straight line. So the geometry is a no-brainer on this one. If you got two things, it's linear. So that is going to be your geometry. It doesn't matter if the two things are single bonded, like in hydrogen. It doesn't matter if the two things are double bonded, like it is in oxygen. Doesn't matter if they're triple bonded, like they are in nitrogen. Doesn't matter if they're the same element or different elements. There's two of them. The geometry is going to be linear, so it doesn't matter. As soon as you see two, geometry is going to be linear, and that's pretty much all you have to worry about with those guys. Now, that'd be nice if everything was like that, but obviously it's not. When you got more than two atoms, you usually will have a central atom. And always, like I said, what you want to look at when you're doing this is always this central atom. So in this case, this is beryllium. And these are really, again, the two things that you want to kind of look at. You want to look at around the center atom, the number of electron pairs. And in this case, that is 1 and 2. Now, something with two electron pairs, the electron pair geometry, again, that's the electron pair geometry, is going to be linear. So what happens is because there's only two electrons, they do not want to be near each other, so they basically just go on opposite ends of the playground, right? Get as far away as possible from each other. They go on opposite sides of each other, and they spread out basically in a straight line, which is linear. When we count this, we also want to count the number of bonds. And when we have one bond and two bonds, something with two electron pairs and two bonds, the molecular geometry is also going to be linear as well. So both the electron pair geometry and the molecular geometry in this case is going to be linear. And the reason for that is we only have bonding electrons here. So as those bonding electrons move, so does the atom that's attached to them. So as they go away from each other, the atom comes along for the ride, and the overall geometry matches the electron pair geometry, which basically again describes how the electrons are arranged around the central atom, while the molecular geometry describes the overall sort of shape of it as everybody kind of moves away from one another. Now, the bond angle here, which they want you to know, is 180 degrees bond angle. Again, if you want to make a chart as we're doing this or just for in the future, these are the things that you want to think about when you look at the central atom. Number of electron pairs, number of bonds. That will give you an electron geometry. It'll give you a molecular geometry and a bond angle. So if you just make like a little chart of those things, you'll be in good shape, and we'll see a chart towards the end as well. The next sort of example here is one where we actually have three things here attached in BF3. Also an incomplete octet happening. We look at the central atom. The number of electron pairs is 1, 2, and 3 pairs. So something with 3 electron pairs is known as trigonal planar for the electron pair geometry. It is sometimes referred to as triangular. So what happens here is we actually have a third electron pair that we didn't have in the last case. So as they are moving away from each other, these guys are going to try to get away. But we then have this problem of these guys don't want to get too close either. So what ends up happening is they kind of have to keep their as far distance they can from all 3 of them. The reason why it's called triangular is they will end up in this triangle type shape there as they kind of spread out from one another. As I just kind of scribbled all over that thing. There, we can't see it. Let's see here. We have, in addition to our 3 electron pairs, we have 1, 2, 3 electron pairs, 1, 2, and 3 bonds. So our bonds in this case is 3. That means our molecular geometry is also going to be trigonal planar. Again, in this case, all the electron pairs are bonding electrons. So as those guys move, so does the bonded atoms. And that gives us basically the same name for both of those, the electron pair geometry and the molecular geometry. It ends up being that kind of equilateral triangle with a bond angle of 120 degrees, basically. So, by the way, the bond angle is associated with the electron pair geometry. So that's sort of where the bond angle comes from. And again, that's about 120 degrees in this particular case. The next sort of geometry is one where we have CH4. Again, looking at the center atom. 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Again, with 4 electron pairs, the electron pair geometry name is tetrahedral. We also have 1, 2, 3, and 4 bonds. With 4 electron pairs and 4 bonds, the molecular geometry will also be tetrahedral in this case. Again, we now have 4 electron pairs, which means as these things move around, they cannot get too close to one another. They kind of have to, again, kind of keep their distance from everybody here. And we get this kind of tetrahedral shape. Has a bond angle of 109.5 degrees. Kind of makes like a pyramidal type shape and also a triangle on the face of it, basically. Any questions on those? Up until this point, when we look at the electron pair geometry name and the molecular geometry name, they are the same, and it's for that reason they have no non-bonding electrons, so no dots on the central atom. So if you draw a Lewis structure and it has no dots on the central atom, and you drew it correctly, the electron pair geometry name and the molecular geometry name should be the same because you are only dealing with one type of electron. You're only dealing with bonding electrons. And as those bonding electrons move, so do the bonded atoms move in the exact same way, and you end up with the exact same name. Now, when we start to introduce non-bonding electrons around the central atom, the molecular geometry name actually starts to change. And the electron pair geometry name actually will stay the same because there's still the same number of electrons around it. But what happens with non-bonding electrons is we no longer have atoms there on those spots. So it gives it a little bit more room to move around, gives them a little bit more room to get away from each other. The end result of that is the overall shape of the molecule actually changes a little as they have a little bit more room to kind of spread out and get away from one another, and we see the actual molecular geometry change. The reason that happens is it has to do with repulsion forces between electrons. So as I mentioned before, electrons really do not want to be near each other because they're negatively charged. So the best situation for electrons and bonding is what we just talked about. Bonding electrons near bonding electrons, that's basically lines near lines, basically, is in your Lewis structure. That's like the best situation. The next best situation, or getting kind of a worse situation, is when you have lone pairs and bonding electrons. So that's when you have dots and lines near each other in your Lewis structure. That's not so great. They're going to try to get away from each other a little bit more. That's going to cause the molecular geometry to change because you have that space where the non-bonding electron is. The worst situation possible in terms of electrons is non-bonding electrons near non-bonding electrons. So dots near dots in a Lewis structure. They have no atoms bonded there. They want to get as far away as possible. So as they start moving, everybody else in the molecule kind of moves with them in the opposite direction to kind of spread out. And we see a pretty dramatic change in the geometry of the molecule because of those non-bonding electrons being involved. So let's take a look and see how this works. So an example of this is sulfur dioxide. And if we draw up sulfur dioxide really quickly here, it looks like this, which I think we did just a second ago. Once again, looking at the center atom is the important one here. And when we count up our electron pairs, we have one electron pair, we have two electron pairs, doesn't matter if they're dots or lines. Again, everybody counts as one. And my double bond here counts as one as well. So that is a total of 3 electron pairs. And once again, 3 electron pairs is the same electron pair geometry that we saw earlier with 3, and that is our trigonal planar. In this case, in terms of bonds, what happens is we got one bond, and once again, double bond only counts as one, so that is 2 bonds. And what happens in this case is we actually have the sulfur that has these non-bonding electrons, and the non-bonding electrons go up, and as it does, those oxygens kind of go in the opposite direction. So they try to keep, again, as far of a distance as they can from each other, but once again, they can't fold too close on the bottom end, so they got to keep a little distance from them as well, because again, that's bonding and bonding electrons now that don't really want to be near each other either. And we end up with a molecular geometry, which I'm going to go with angular. Now, some people will call this still bent, and some people will call this bent angular. And I'm going to go with angular because truly the bond angle here is a little bit different than what you'll see with bent or V-shape like you see in water. And in this particular case, our bond angle is less than 120 degrees. So again, the bond angle is based off a trigonal planar, which is 120 degrees. Because we have the non-bonding electrons, it's able to move a little bit more, so it's a little bit less than 120 degrees in terms of its bond angle. Any questions on that one there? Next example is ammonia. And ammonia, if we look at the central atom, has 1, 2, 3, and 4 electron pairs. Once again, something with 4 electron pairs. The electron geometry is tetrahedral. In terms of bonds, 1, 2, 3 bonds. So something with 3 bonds and 4 electron pairs. Similar thing happens. The non-bonding electrons come up. The hydrogens go down to try to keep as far of, again, a distance from everybody as they can. And we end up with a molecular geometry of trigonal pyramid, or pyramidal, depending on your book. And that is because it kind of makes a triangle and this pyramidal shape coming down on the bottom there. And this has a bond angle as well of less than 109.5 degrees. It's like 107-ish, I think, for this particular one. And again, it is based off of the tetrahedral geometry, electron pair geometry. Question on that one. Important note here, we saw earlier trigonal planar, which is 3 electron pairs and 3 bonds. And this is trigonal pyramid. They are different geometries, and you need to state the second word there. Do not on an exam just put trigonal and let me choose because I'm going to choose wrong. Yes, and put an X. Do not do my other favorite thing, which is I'm going to write trigonal here confidently. And then, that's like a planar, pyramid. You can clearly see those right in there, right? Both of those are going to get an X, yeah? So if it's planar 3 and 3, make sure you write it. If it is 4 and 3 there, trigonal pyramid, again, they are different in terms of their geometry. Any questions on that there? Last geometry, which I'm not sure where it went, but we'll do water. So when we look at water and we look at the central atom, we have 1, 2, 3, and 4 electron pairs. And 4 electron pairs, the electron geometry is still going to be tetrahedral. In this case, though, we only have 1 and 2 bonds. And in the case of water, all bad things are happening. We have non-bonding electrons near non-bonding electrons, which definitely do not want to be near each other. As they move away from each other, those hydrogens come out this way and also moving away as well, but not too close. And that gives us a molecular geometry of bent or V-shaped. And this is why we're going to use bent or V-shaped for water, this situation, rather than for the angular situation that we saw with SO2, because the bond angle here is less than 109.5 degrees, kind of like 104 in this case of water. That is also why you see water typically drawn like that in this kind of bent or V-shaped when you see it kind of drawn. Question on that there. So in your book, you have a table just like this, and it's basically based on number of electron pairs and bonds, and that's really the good way to learn it, electron pair geometry and molecular geometry as well. The one that's not up there is SO2 that we talked about there, that angular. You need to make sure you know that one as well. Any questions on that there? Okay, so let's talk